So the conductor, remember, let's make it a solid. If we could somehow magically inject some extra electrons into the center of this solid conductor, what's going to happen to them? What's the definition of a conductor? Charges are free to move, yeah. What happens to all those electrons? They're all the same charge. What do they do to each other? Repel each other. So they want to get as far away from each other as possible. So where do they end up? All over the outermost surface, evenly distributed over the outermost surface. So any excess charge on a conductor in static equilibrium, always the excess charge always ends up on the outermost surface. This is for charges that are in equilibrium. If we put an electric field on a conductor and they're moving, that's different. In the wires in our walls that carry current, the current is not all on the outermost surface of the wires. It's through the cross-sectional, it's uniform over the cross-sectional area of the wire because they're moving around. It's not in equilibrium. But if we take the electric field off, any excess charge is eventually, they're going to push on each other and distribute themselves uniformly over the outermost surface. They want to get as far away from each other as they can. That's for an object that has a uniform shape to it. If an object has a non-uniform shape, like a peanut, or whatever that is, and we've stuck excess charge on this, it actually distributes such that the charge where the radius of curvature is the smallest, you get the most charge. And there's a reason for that. The reason is, we've already started to dip into the next chapter, electric potential. The reason is a conductor is an equipotential surface. Every part of the surface of a conductor is the same potential, the same electric potential. And so because the radius of curvature is different, you have to have a higher charge density on the smaller one to get the same potential as you do on a bigger one. We'll get into that shortly. Maybe an easier way to picture it is this. If we take a sphere and another sphere, one with the smaller radius, one with the bigger radius, and we connect them electrically with a wire, now this is all one conductive surface. The small sphere, the wire, the big sphere, it's all one electrically conductive surface. It all has to be the same electric potential. And so we'll see very shortly that the smaller one has to have a greater charge density to get the same potential as the other one. So we'll talk about that in a little bit. But that's what's happening. And that's why if you have a pointy object, you get a very strong electric field. The electric field lines come out like this. Right, if this object has some positive charge on it. The electric field lines come out like this. So where are those field lines the most dense? At the point, right, at the tip. That's where the strongest electric field is. Lightning rods are designed this way. very strong electric field at the top. A lightning rod, its purpose is actually to prevent a lightning strike. Because the electric field can be so strong right there, the charges can actually bleed off. And the object that it's connected to, you can actually lose some of its excess charge. Because what causes a lightning strike is a charge difference, right? The charges build up. And so if you can get some of those charges to dissipate, then you can prevent a lightning strike. So that's the first purpose of a lightning rod, is to prevent a lightning strike. The second purpose is, if it can't prevent it, to make sure the lightning hits that rod, because the rod is grounded and it avoids damaging the building. So that's why you can sometimes prevent the lightning strike by getting the charges to bleed off at that area where you have a very high electric field right in there. Or if the lightning does strike, it's attracted to that tip because that's where the strongest electric field is, and it can be diverted to ground. Okay? So that kind of wraps up the previous chapter. Shielding, the fact that you always get that zero electric field inside of a conductor in static equilibrium because the charges are free to move, right? If the electric field wasn't zero in there, more charges would move until it was zero. So electric field zero inside of a conductor, even if there's a cavity, even if there's a hole inside the conductor, still has a zero electric field in there. Okay, so let's get back to our electric potential worksheet we were working on yesterday, or